Okay, welcome back. So, we have quite a few classes here. Let's see what they do. So, it's a predator-prey simulation. We need a predator and we need prey. So, the fox class is a hyper-simplified model of predator, and the rabbit class is the simplified model of the prey. The simulator class is responsible for managing the overall simulation, and as such it needs a collection of foxes and rabbits, and it's going to need to know where those foxes and rabbits are in the grid, and it's going to have to rely on some other classes to actually visualize that. But the simulator is kind of where this is where we tell the foxes to do their thing and tell the rabbits to do their thing is going to come from. There is a field class. A field is a two-dimensional representation of locations, and a location is an individual position inside of that field. There is a simulator view, which will go and look at that field class and draw a visual representation of the different locations depending on if it houses a fox or a rabbit or is empty, on the basis of the way the behaviors are defined in the simulator. So on a step-by-step basis, simulator view is responsible for the visual representation of the simulation. There is also the field stats and counter classes, which are maintaining step-by-step statistics, which will be useful. And then there is a randomizer class, which is pulled apart from everything else. The importance of the randomizer class is so that if every class was responsible for producing its own random number, the challenge with simulations would be that you want to be able to set things up so that you can test your assumptions and know that the assumptions are being tested with the same initial conditions before you actually go to full randomization. Because there are no such things as truly random numbers in computers, it is possible, if we're using a single randomizer class, to feed it with a known seed value so that the resulting sequence of requests for random objects and numbers will be consistent. Put another way, if you have two different random objects, but you seed them with the same initial value, they will return the same results in the same order every time, because the numbers inside of the randomizer class are only pseudo-random. We rely on the fact that we give it a seed that we don't know, and therefore the values appear random to us. But if we could put the exact same seed value in, we would get the exact same results out. Let's go and take a look at what the visualization looks like. So if you run the simulator, you'll get a field, and the field will have a step count at the top and a population count in the bottom status bar with the number of rabbits and foxes. Rabbits are represented by orange squares, and foxes are represented by blue squares, and empty field elements are represented by white squares. And so the visualization gives us a sense for how this field currently exists. We can tell the simulation that we want to run a step, and in order to do that, it's going to need to manipulate the state of the rabbit objects and the fox objects. So let's look at what a rabbit knows. A rabbit's state is made up of the current age of the rabbit, whether or not the animal is alive or not, what is the location of the rabbit, what is its location data inside of the field, and what field that location exists in. And then there are a bunch of methods. The rabbit's behavior is managed via the run method. So rabbits run. When we have a rabbit run, we increment its age, and every rabbit has a consistent maximum age, and if they reach that age, then they expire. If they are not of the age where they die, then rabbits have a chance of breeding, and new rabbits might be created at that point. Now, there are obviously some simplifications here. In effect, all rabbits can produce offspring in this model, so all rabbits are female. Also, the rabbit could breed on every step of the simulation, so there's no gestation period. There's no downtime. And of course, there's a reason why the phrase is they breed like rabbits, because rabbits are prolific breeders, but they can't breed every step if the time step is supposed to be every day or even every week. So, this could be a simulation that throws off a choice for the simulation that throws off some of the results. Also, all rabbits die at the same age. If you've seen Logan's Run, that 1970s sci-fi movie where people have a indicator embedded in their I think it's in their palm. When that flashes, they've reached the age where they're supposed to report to extermination chambers. And so, like, you can imagine little red jewel-toned things in a rabbit's paw, where if it flashes, it knows that it's time for it to expire from the simulation. Probably not a realistic, definitely not realistic, but does it have a negative impact on the simulation would be the question. When you look at the code, or look at the way the code is laid out, do you see other simplifications in the way the rabbit is implemented? Think about that and be ready to write it down for the homework. While you're thinking about rabbits, though, let's take a peek at foxes. A fox also has an age, also knows whether or not it's alive, also has a location, also has the field that the location is in, and has a food level. What a fox does is it hunts. Its main action is hunting as the predator in the simulation. But foxes also age, they also breed, and they become hungry, and they hunt for food in locations that are adjacent to them. So we have some additional constraints on the way a fox behaves here. Looking at foxes, there are similar simplifications. If a fox gets to a certain age, it will expire at that age. If a fox, all foxes are female, so all foxes could effectively breed. And if the random number generator returns results, they can breed on subsequent steps. So, we have those simplifications. But also the way they hunt is also somewhat simplified. Do they hunt on every turn? Should there be a point where, if they've satisfied their hunger, that they will take some time off and not need to hunt? So there's some things that could be added into the simulation like that. The question is, are simplifications ever acceptable? And the answer is simplifications are inevitable. It just becomes a question of, are you aware of the impact of those simplifications, and can you communicate that to the person who is relying, or people, policymakers who are relying on the simulation that you're making. Okay, let's look at the simulator class. Three main things about the simulator class. So we set things up inside of the constructor, and there's a populate method which gets the initial setup for the field. So each animal is given a random starting age, because if they all started at age 0, then the entire population would die out at one time. We don't want that to happen, so we need to seed the population with a random start. And then we have a simulate one-step method, and it iterates over collections of foxes and rabbits. And what we end up doing is we have the current field, and then when we're running the simulation, the information that is happening in the current field on the step gets written into the updated field. And then once we leave that step, what was previously the updated field becomes the current field for the next step. So let's look at what updating involves. We're going to use iterators inside of a for loop. We're using iterators because objects might need to be removed from the collection at this point. So grab the iterator from the rabbits collection at initialization, and we're going to keep in the for loop as long as the iterator has a next object. While it does, grab the next object from the collection and put it into the variable rabbit. We tell that rabbit to run, do its thing, and get new rabbits back from that process. And then if the rabbit is reported as no longer being alive, remove it from the collection. Once we process all the rabbits, we will then process all of the foxes, ask the fox's object for its iterator. While it has a next fox, grab the next fox, put it into the variable named fox, tell the fox to hunt, and also to potentially generate new foxes. And then if the fox is not alive at this point, remove it from the collection. And if you look at these two blocks of code, you can see they're remarkably similar. In fact, whenever we see blocks of code that are doing the exact same thing, we usually start thinking there's a better way to structure this. But there's also a problem. Fox and rabbit, while they have strong similarities, they don't really have a common superclass. One is predator, one is prey. Fox has a hunt method, rabbit has a run method. But the update step does involve similar looking code. And I guess from a coupling standpoint, the simulator class needs to know that the fox is a predator because it has to call hunt, where it has to know the rabbit is prey because it has to call run. So think about what we might do to fix that. When we come into the next portion of the lecture, we'll move forward and implement some changes.